Okay, so this is where we stopped last Tuesday. Okay, so as a recap, so we cannot move directly the data, the value to the data segments registers. Okay, so how to do that? We need to first move that into any other registers. There is non-segment register, and then only we can shift that, okay, we can move that to the data segment register. All right. Okay, so this is we already discussed, okay, about whether if the where data is larger than 8 bits, so it cannot be moved to the register that is 8 bit. Okay, but for 16 bit it is okay as long as the data is 16 bit or less. Okay, so for the addition, we also discussed on Tuesday. So we know that the general purpose register is the accumulator, okay, because it can do the addition function. Okay. All right. So we have three. So the assembly language, we have three segments, which is the first one is code segment, second is data segment, and then the third one is the stat segment. Okay, so we already discussed about that, what function of each of the segments. So we already learned about what is our logical address, what is the offset address. Okay. So are you guys clear with the concept of logical address and the segment physical address? Okay. All right. So we also discussed about on how to add, let's say, the location from the register into another register, but we don't want to add the value, so we use the bracket. Okay. Okay, let's look over here. Okay, let's say we have an example. So here bx, we use it as a pointer. All right, first we want to initialize our register AL, so which is an 8-bit register, which is the general purpose register. So we put 0 on the AL, and then BX, we want to move a value of 0200. Okay, so here the BX points to offset address of the first byte. Okay, and then add the first byte to AL. Okay, so we add that value 0200 to AL. Okay, and then INC. INC is increment. Okay, so we increment BX to the point to the next byte. All right, and then now of course the BX will change, right? So it will move to the next byte, and then at the next byte AL. Okay, and then we increase again the BX. Of course, it will add to the next byte. Okay, and then it will increase. Increment is 1 by 1. All right, so we keep increase that. Okay, how many times? 3 times. Okay, so the INC, the increment instruction, adds 1 to the operand. Okay, so the example is we achieve the same result as the addition of value of 1 to that register. Okay, for example, INC BX is similar to add space BX, comma 1. Okay, the physical address for data is calculated using the same rule for the code segment. Okay, so for the physical address of data is calculated by shifting DS, okay, the data left 1 hex digit and adding the offset value. Okay, so we look for the example. Okay, let's say we have the D as 5,000 and the offset is 1950. Right, so we need to calculate the physical address. Okay, so how to do that? All right, so we have the offset is 1950. So as you remember that in order to have physical address, we need to shift 1 hex digit. Right, so the DS will be 5000. Okay, and then we add that with the offset, so it will become 51950. Okay, so that's how to do that. Okay, all right, so let's look for another example. If we have DS 7FA2 and then the offset is 438E. Okay, first we need to calculate the physical address and then its lower range and also the upper range of the data segment. Okay, and this shows the logical address. Okay, so how to do that? So it is, okay, so we shift that. So 7F82 and then we add a 0 because we shift 1 hex digit and then we add with 438E. Okay, so it will become 83DAE. So everyone is clear with that? Okay, so this is simple to find the physical address. And then how about lower range? As I said, for the lower range, so we take the DS and then we add 0000, which is 4 bit of the hex digit. Okay, so that is we still obtain 7FA2 0. Okay, and then for the upper bit, so we add with FF. So it will become 8FA1F. Right, and then the logical address. So this is the easiest one. So we just put double dot between 7FA2 double dot 438E. Okay, all right. So we look for another example. Assume that the DS register is 578C. Okay, to access a given byte of data at physical memory location, okay, 67F66. Does the data segment covers the range where the data resides? Okay, if not, what the changes to be made? So how do you know whether that number is covered or not? So we must look at the lower range and upper range of the data segment. All right, so how to do that? So of course, we need to shift 578C 1 hex bit, so it becomes 578C0. And then we add that with 0000. Of course, it will still be 578C0. Okay, and then for the upper range, we need to add with FF. So it will become, okay, 678BF. Okay, so you notice that location is much smaller than the proposed memory location at 67F66. Okay, because that's not within that range. So to access that byte, so the data segment register must be changed so that its range will include that byte. Okay, so we need to change that value so it can cover until that memory location. All right. So we look at the little endian. So little endian convention. So what is that? So previous example, we used 8-bit or 1 byte of data. What happens when 16-bit data is used? For example, we use AX. Okay, so over here, so we the value of 35F3 into AX. Okay, and then that value of AX is offset. Okay, if offset to the data at the data segment of location of 1500. Okay, so you add to the offset. So from there, okay, so from there, you can actually use that memory location to put with some another data. Okay, so we look here. This memory location. So we have right now, okay, the low byte goes to the low memory location, okay, and the high byte goes to the high memory location. Okay, so over here, so we have the 16-bit. All right, so we have the DS1500. So where the two lower bit, all right, so with the two, sorry, that's for the 8-bit. So for the 8-bit, that is based on the lower 2-bit. Okay, so we add that to the DS location of 1500, okay, which is the F3. And then for the 335, we add that to the higher memory location of the data segment, which is 1501. Okay, so that 1501 now contains the value of 35. Okay, so this convention, okay, is called the little endian and versus the big endian. Okay, so this is come from the Gulliver's Travel story about how an egg should be opened. All right, from the little n or the big N. Right, so because the egg has actually has both ends, so that end, so you know the egg, so the egg will be curved. Okay, it will not be a circle. So if it are a circle, so at any end you can open it, but because the egg is in oval shape, so on the oval shape, so we can either open it on the big end, all right, the big end or the little end. So how we should open it? So that's the name, how the names come from. Okay, little endian and big endian. So the big endian refers to the higher memory location, and the little endian refers to the lower memory location. Okay, so this is what I mentioned. So the high byte goes to the high address, okay, and the low byte goes to the low address. Okay, let's look for example here. We assume that memory locations with the following content. So let's say we have the data segment at location 6826, we have the value of 48, and then for the higher location, we have at 6827 with the value of 22. Okay, so show the contents of register BX in the instruction. So we want to move the value of 6826. Okay, so according to the Little Endian convention used in all 86 microprocessor, the register BL should contain the value from the low offset address of 6826. Okay, and then the register BH value from the offset address, okay, 6827. Okay, so over here, so we have the value of DS. So DS 6826 contains S48. All right, and then DS 827 contains the value of 22. So the content of 22 will go to the BH, and the lower content will be 48. Okay, so that should be easy. All right, so the all Intel microprocessors and many controllers, the Little Endian convention. For example, Freescale, so formerly Motorola microprocessors, along with some other microcontrollers use big endian. Okay, so Motorola use the big endian, but the Intel and also other microcontrollers use Little Endian convention. And for the we have also the extra segment. Okay, so the extra segment register, which is part of the data segment register. Okay, so we have the extra segment register is used as an extra data segment. Okay, so in many normal programs, segment is not used. So it is used for the essential for the string operation. So for string is like what we write. Okay, so it's like we want to write a statement, then we use the string operation. Okay, so to map the memory into the IBM PC, so let's say for here we have the 20-bit address of 86 processor, which allows of 1024 kilobytes of memory. Okay, with the address range cost from 00000FFFFF. Okay, and then during the design phase of the first IBM PC, the engineers had to decide on the allocation of the 1 megabyte memory space to various sections on the PC. Okay, so this is what is called as the memory map. Okay, so we need to decide how to allocate. So we have 1 megabyte of memory, and then how we want to distribute. Okay, how many parts? Let's say we have 1 megabyte, and then let's say we want to have 128. Okay, 128 goes to which section? All right. So that is called memory mapping. Okay. And then let's say we have originally in the RAM. Okay, you will just want to put 640k into the RAM, and then we allocate another 256k for the ROM. Okay, so this is in terms of the memory allocation. So you can see that the range of addresses that can be gathered by the segments inside the PC. Okay, so for example, for the RAM, if we have 640k of memory, so the maximum location that can be stored is at the number 9FFFF, right? And then after that, we allocate another segment of that memory, so to another for the video display. So that is for another 128k. So it starts from the address of A0000. Okay, that is after 9. Okay, so after 9 we have A, and then F will become 0. Okay, so that is exactly after that RAM. Okay, and it stop at BFFFF, and then the ROM starts at C0000, and then it ends to the FFFF F, okay, which is the maximum memory space allocated for 1 MB. Okay, so right, so this is what I just explained. Okay, so in the early 80s, most PCs came with 64K to 256K bytes of RAM, so which is more than adequate at that time. Okay, so the users has to buy memory to expand up to 644K, 640K. All right. So managing the RAM is left to Windows because the amount of memory used by Windows varies, and then the different computers has different amount of RAM. Okay, so because we are using the Windows OS, so basically the needs for the RAM depends on the application inside the Windows that we use. Let's say we use the Adobe Photoshop. Of course, it will require a lot of RAM because it requires graphic processing. So we need to store many image information before it's transferred to another location. That's why when we involve, if we deal with the graphics software or graphics application, we need to deal with the huge amount of RAM rather than the application is in terms of text. Okay, so that's the variation of RAM that is needed for different kind of software. Okay, so for that reason, we do not assign any values for the CS, DS, and SS registers. Okay, so we keep the data segment stack segment, and all right. So the data segment register, so we keep it of the reason. Okay, because of the reason, because we want to have RAM. Okay, is made Windows. Okay, so such assignment means specifying an exact physical address, okay, in the range of 0000 to 9NFFFF. Okay, all right. So we allocate that. That means that amount, okay, that amount is allocated inside the RAM. Okay, so for this amount, that one can be used for CS, ES, or SS registers. Okay. All right, so from A000 to BFFFF, so that is used for the video. Okay, so this is depends on the amount used and the location on the video board installed on the PC. Okay, and then as you remember, for the video processing, so we have usually the user can add the external graphics card. Okay, that's for the video processing. So if we add the graphic cards, because of course we need to have the graphic card because nowadays we have many, we want to see many beautiful screen, many beautiful images right on the screen with user-friendly interface and so on. So we need to have a huge amount to be stored in the data into the memory. So that is why we need to have usually for better graphics processing, we need to have another GPU or graphical processing unit, or there is another microprocessor for the graphics. Okay, so we install this in the external card for usually. So this card is also actually this category based on the processing speed and also based on the allocated memory space. So for example, we have 1 GB of the graphics card. Probably we have the 4 GB of graphics card. Okay, so this amount varies depending on that installed on the PC. Okay, and then from the C000 to FFFFF, so that is set for the ROM. Okay, so not all memory in this range is used by the PC's ROM. Okay, so 64 kilobyte from the location. okay, FFF000 and FFFF are used by BIOS. Okay, so that is the end part of that data segment. So we have starting from C000 to FFFF, and then starting from F000 to FFF. So that is used for the BIOS. Okay, that is the basic input and output system ROM. Okay, so for other remaining space is used by various adapter cards, okay, such as a network card, and the rest is free. Okay, so for example, maybe later you add another devices such as the wireless keyboard, for example. So you need to have that space on the memory spared for those devices. And let's say, for example, you want to add multiple cameras to your PC, or you want to add another monitor. Okay, so let's say you want to have, now you have only one monitor. Later you want to have, let's say, 3 monitors to be connected. So you need to have space for the instruction to be set, to be given to that monitor to function. So that instruction needs to be stored inside the ROM. Okay, so only that way then the monitor, another extended monitor, can work. Okay, all right, and then 640 kilobytes from 000 to 9FFFF is referred as the conventional memory. Okay, so this is on the RAM. Okay, so this is the conventional memory. So the 384 kilobytes from the A000 to FFFF are called the upper memory block. Okay, so upper memory block, like we said, we use for the video processing. Okay, so for this one, okay, so we use for the video processing, okay, video display. So that is upper memory block. All right. Okay, so there must also be some permanent non-volatile memory to hold the programs, telling the CPU what to do when the power is turned on. Okay, so that collection program is referred to as a BIOS. Okay, of course, you need to start with the BIOS first, and then you can instruct. Okay, BIOS will instruct for you to, okay, now start the Windows. Okay, Windows is the operating system. So we start with BIOS. Okay, BIOS will instruct you to start the operating system. What if our operating system is corrupt? If Windows is corrupt, we still have the BIOS. Okay, but if BIOS is corrupt, of course, your uh, your computer will not be functioning well. All right, maybe you cannot even turn on your computer. So how to solve that problem? So you need to reflash your BIOS. Okay, so you need to reflash your BIOS. What if you cannot flash your BIOS? All right, so that will be a trouble for you because you cannot use that computer anymore. All right, so the BIOS stands for the basic input and output system. So it contains program to test the RAM. So check whether the RAM is in good condition or not. So whether it have a back segment or back sectors or not. So if we have back segments, then how can we use that location to store the RAM? Okay. So it will test other components connected to the PC. Okay, so it also contains programs that allow Windows to communicate with peripheral devices, and then the BIOS test devices to connect to the PC when the PC is turned on and to report any errors. Because when in the BIOS, you want to also making your keyboard working, okay, making your mouse working, right? So that's why the BIOS is important. Okay, all right, so I'll stop here for today. Okay, so we will discuss about the stack, okay, which is the stack segment next week, all right? Okay, so I hope it is clear for today's discussion. Okay, so before the session, so let's turn on camera, everybody, so we can take the picture together. Come on, everyone. Okay. All right, so I'm going to count from 10. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, please smile, everyone. Okay. All right. Cheers, everyone. Okay. Okay, so I see you again next week. All right, so that will be your 4th week. So remember that you're gonna have your test 1 exam soon. I'm going to give you assignments later by Sunday. Okay, I'm giving you some assignments. Okay, so you need to finish that. So as the exercise for your test, right? For your test 1. So might be we're gonna have our test 1 in the 5th week. Okay, so that will be covered until the introduction of the assembly language. All right. So we still haven't finished with the introduction of assembly language. Okay, so we will try to finish that by Tuesday. Okay, so you need to remember what you have learned so far, right? So any question before I stop the session?
Not at the.
No, no.
Okay. Okay, so all right, so that's it for today. Okay, thank you everyone. So have a good weekend. Okay, it's still early.